This is part 13 of the series Logarithmic, Exponential, and Other Transcendental Functions. In the last part, we worked these last two examples of applications of exponential functions, and now I'd like to continue on and do another type of example. In this problem, it's a compound interest problem. We have $2,500 deposited in an account that earns 5% annually. We want to find the balance after 5 years with the following compounding schedules. We want to compound quarterly, then monthly, then continuously. So let's take a look at what that would look like. This is a fairly straightforward application. That's all we have to do is substitute into our base formula. Our final amount is equal to the initial principal times the quantity 1 plus annualized interest rate at 5%, that's 0.05%, divided by four compounding periods quarterly, 4 times a year, and that whole thing is being raised to the power of the number of years, 5, times the number of compounding periods. We put that into our calculator and we get approximately $3,205.09. Now when we change the number of compounding periods from quarterly to monthly, 12 compounding periods per year, everything else stays the same except that 4 goes to 12 and that 4 goes to 12. And you can see that the exponential has changed. The exponent here has changed, gotten a bit larger from 20 to 60, and it increases to 32.08 and 40 cents. Now the last one is compounded continuously, and this is our P(e) to the r times t. So principal, e to the interest rate times the number of years. And that generates $3,210.06. So you would think that this would get much larger, but it doesn't, because this function being asymptotic to 2.71828, it doesn't just continue to increase without bound here. So you can see clearly that continuous compounding is superior to these other compounding periods, but it's not what we might have expected. All right, let's look at another example. Now this example is more or less a recap, a refresher of what we've done in the past. We want to find the derivative of f of x. This is an exponential to a base other than e, so it would probably be simplest to convert this to an exponential with a base of e. So we rewrite f of x as e to the ln of 4 times x. Then f prime of x is e to the u du. So the derivative of ln of 4 times x is just ln of 4. And then we convert our base e exponential back to the base 4, and we have 4 to the x times ln of 4 as our final result. All right, let's look at another one. Here we have just a slightly different twist. We have a power and an exponential to a base other than e. So see if you could figure out how to do that one. What I did here is I kept the power expression the same, and I changed the exponential to have a base of e. Now we got to be careful here, because this is the product rule, and with the product rule we have a u and a v term, but unfortunately we've got this guy, so we're going to have a substitution. Now normally we would say it's e to the u du, but I just don't want you to get confused with this u and this u, because this is u and v for the product rule. So we're just going to say the exponent here instead of making this our u. So the product rule says u dv plus v du. So the u comes down here, and the derivative of this is this whole thing times the derivative of the exponent. The derivative of ln of 2 times t is just ln of 2. So this is u dv plus v, we just rewrite this here, times the derivative of our first term here, u, which is 2t. Now if you'll notice, we have e to the ln of 2 times t in both of these terms. So I'm going to factor that out. So I'm pulling out an e to the ln of 2 times t from both of these. What we're left in the first place is t squared times ln of 2 plus 2t. This comes down here. That's factoring out this term and this term. Then we can convert this outer term back to our base of 2 exponential and leave this the same, and this is our final value. All right, let's take a look at one more example. In this problem, we have a product of 2 to the negative theta, that's an exponential, to a base other than e, times cosine of pi theta. So we have two variable expressions here multiplied together, and we want to find the derivative with respect to theta. So now theta is a variable as opposed to being x or some other variable. Now my first preference would be to convert this guy to a base of e, an exponential with a base of e, and see where that leads me. This is, either way, this is going to be the product rule. So let's see how this works. Here's my conversion. 2 to the negative theta is e to the ln of 2 times negative theta times the cosine of pi theta. Now to take the derivative, again, this is going to be the product rule. So this is our u term, this is our v term. So u here, dv. Derivative of cos pi theta is negative sine pi theta times the derivative of the inside piece. Remember the chain rule. So it's the derivative of the outside times the derivative of the inside. So that's u dv plus v, this cos pi theta, times the derivative of this exponential here. And the derivative of the exponential is just the entire exponential, that's this guy, times the derivative of the exponent. And since negative theta is our variable term, the derivative of ln of 2 negative times negative theta is just negative ln of 2, because ln of 2 is a constant, and this is our variable term, which drops out. And so this gives us the final result here. Notice again that we have this e to the ln of 2 times negative theta term in both terms. We have one here and one here, so I'm going to factor that out. So here's that term factored out. And what we have left when we divide this by e to the ln of 2 times negative theta is negative sine theta, negative sine pi theta times pi, which is this guy, minus, because notice the negative sign here, this negative ln of 2 is being multiplied by this, so it's minus cos pi theta times ln of 2. Now I can go ahead and convert this back to 2 to the negative theta, and I'm pulling out a negative 1 from here as well. So if we pull out a negative 1 from this guy goes positive, this guy goes positive, and the sign comes out front as negative. So a little bit more complicated, but it's the only complication comes in with this guy. It just allows us to differentiate something that ordinarily wouldn't be differentiable. All right. Well, that wraps up the examples of applications of exponential functions and integration and differentiation of exponentials and exponentials to bases other than e. Now we're going to head into a fairly major topic, and that is going to be the differentiation and integration of inverse trigonometric functions. So we're going to give an introduction to this in this video and finish it in the next. So let's go ahead and introduce this concept. Now, as you will recall, there are 6 basic trigonometric functions. There's sine, cosine, tangent, cosecant, secant, and cotangent. Each one of those has an inverse function. Now, what we're going to do is we're going to take these apart one at a time, And our goal is going to be to determine the domains and ranges of each of the basic 6 trigonometric functions as they relate to having an inverse function. Recall a couple of videos ago that we had a discussion on inverses and functions that have inverse functions. And so we're going to be revisiting that in this video here. So let's start with sine. Now you know that sine is cyclic and periodic. It has a period of 2 pi radians, but there is a restricted interval on which sine has an inverse function. You'll notice that if the horizontal line test fails, if we had had the function continuing down like this, a horizontal line here would cut the graph twice, which would mean that at that point sine would not have an inverse function. So we had to restrict the domain. And where we restrict the domain is we're taking sine from negative pi over 2, that is approximately 1.57, to pi over 2. So on the interval negative pi over 2 to pi over 2, sine does have an inverse function. And if you take a look at the nature of inverses, when they reflect across the line y equals x, the x's and y's swap places. So this point, 1.571, becomes this point, 1.57, or pi over 2, 1 becomes 1 pi over 2. This point, negative 1, negative pi over 2, becomes negative pi over 2, negative 1. So the domain of sine becomes the range, the y value of arcsine. So you can see that arcsine is the white and sine is the yellow. And that's going to be the same for all these functions. So we can see that the domain for arcsine is negative 1 to 1. It's defined on that interval from negative 1 to 1. And its range, its possible outputs, is negative pi over 2 to pi over 2. So negative pi over 2 to pi over 2 here. For cosine, cosine is here. Again, cosine is cyclic, so it's continuing like this. And if we draw a horizontal line, it doesn't have an inverse function in this interval. Likewise, over here, it wouldn't have an inverse. So we have to restrict the domain, and where we restrict the domain is from 0 to pi. So if the domain of cosine is 0, 1 to pi, negative 1, so the domain is 0 to pi, the range of arc cosine is 0 to pi. And if the range of cosine is negative 1 to 1, then the domain of arc cosine is negative 1 to 1. So again, you can see that they reversed each other. So here is the domain of arc cosine. Negative 1 to 1 and range 0 to pi. And now for tangent. Tangent's a little easier. Tangent has a domain of negative pi over 2 to pi over 2. So that gives the range of arctan. You can see the white function is asymptotic at pi over 2 and negative pi over 2. And so that makes our domain and range pretty easy. Since the range of tangent is negative infinity to positive infinity, the domain of arctangent is negative infinity to positive infinity. And the range is negative pi over 2 to pi over 2 because that is the domain of tangent. All right. Well, that's just a brief introduction. We're going to continue this in the next video with cosecant, secant, and cotangent. So I will talk to you in the next video.